Okay, so today we are going to talk about the greatest use for the concept of equilibrium. So remember that equilibrium in chemistry is the study of the extent of a reaction. And what we mean by the extent of a reaction is, in other words, the question would be, does my reaction want to make products, or do my reactants want to stay as reactants? And so remember when we originally talked about KEQ, we talked about K having two different identities. Either K is greater than 1 or K is less than 1. Do you remember what a reaction means if you have a K greater than 1?
Is it product beta?
You got it. And we know this because when we're writing our K, we have our products on top and our reactants on the bottom. And so if this number is greater than 1, the only way for that to happen mathematically is for the product numerator to be greater than the reactant denominator. That's just simply how a fraction works. And so then the opposite is true if K is not negative, but less than 1, it is reactant favored. So today we're going to apply what we learned last time with the KSP, and we're going to learn apply what we know about these two properties of the K value, and we're going to talk about how we can do calculations about the equilibrium constant. Do you need something, Elliot?
Yeah, I've seen tissues.
Oh, they're on my desk.
Oh, sorry.
That's okay. So today's topic is called ice tables. Gentlemen, language.
Joe's being racist. I was not.
Oh, check your racism. All right, so, that would have been a smart thing to do, but here we are. All right, so the ice table is something that is a useful tool in determining equilibrium concentrations. An ice table is a useful tool in determining equilibrium concentrations. Okay, so why are equilibrium concentrations important? This is what you need. So, in other words, what you need to calculate KEQ. God bless you. Okay, so on homework number 8, when we first talked about the equilibrium constant concept, I made you practice writing KEQ for different equations. We got good at that. And then the rest of the homework was you putting numbers into the formulas and determining what type of reaction you had, if it was product or reactant favored. I had given you those numbers at that time. But now we're to the point where we are more advanced as chemists, and now we need to figure out what those numbers are to put into the K equation. Okay, so this is a multi-layered step thing. The instructions on your homework on a test are very brief, but the number of steps that you have to go through is lengthy. So I'm going to break all of the steps of this process apart, and then we will do some practices of it, and hopefully that will help us to know what we're doing. Okay, so before we do that, let me just show you what an ICE table actually is. Okay, so I'm going to use a regular chemistry chemical equation, and I'm going to use this to show us what an ICE table is. ICE is a word, but it's also an acronym. It stands for initial, change, and equilibrium. So here is my chemical reaction. Sometimes some teachers will call it a rice table because R is the first line for the reaction. That's fine, but that's not how I learned it, so that's not how I'm going to teach you it. I stands for initial. So what is happening at the beginning before things have done any reacting? And so I'm making these numbers up off the top of my mind.
Should we write this down?
Yes.
Oh, shit.
The reaction. I thought this just
Yes.
was, I thought
You
this
should.
was just
If
an
I
example.
put it on the board, you should put it in your notes.
Alright, can we pause for it?
All right, so where am I getting those numbers from? I'm making them up off the top of my brain. Most of the time, not always, but most of the time, you're told the quantity that you're starting with for your reactants. Now, at the initial part of the reaction, it means that the reaction hasn't started happening yet. So how much product do you think we have? Before these two things interact together, how much product is there? Mason? 0. Because it hasn't started yet. Most of the time, on your I line, you will have a 0 for your products because nothing has yet happened. For those of you who will be taking AP Chemistry next year, we will see where there are exceptions to that. The second row is the C, which stands for change. In the second row, we're going to determine how much of our chemistry is going to happen. Now, we will go through many examples of this, but the change row has to make sense stoichiometrically. So, let's imagine that I should have used simpler numbers, but that's okay. Let's imagine that 0.0138 mole of my H2 has reacted. So now all of the stoichiometry has to make sense. That means that if I've used this much of reactant 1, I have to use, that same amount of reactant 2. Why? Because their stoichiometric coefficients are the same. In the same way that if you were making a sandwich, if that was your chemical reaction, and for every one piece of bread you used one piece of cheese, you should be using the same amount of bread and cheese for each time you're making a thing. But now we have to think about what we're doing to the products. Every time we use one H2 and one I2, we're not making one HI, we're making 2 of them. So that means that my numbers should look like this. Copy this down and I will explain more about this. In the change row, always, your reactants will be minus. Why? You're using them up. So when you use pieces of bread to make your sandwich, they're gone from the bag of bread, right? Same thing for reactants. If you're using H2, that means that you have to subtract it from the amount that you originally started with. For products, however, you're always going to have an adding sign because You are making products, you're not using products up. Does that make sense? How I got that? Okay, good. So those are the first two rows of your ICE table.
Are the red numbers random numbers too?
Yes, I just made those up.
Okay.
All right, so now the E row, I usually draw a line after it, after the C row, because E does not stand for end, it stands for equilibrium. And so now in each column, for each species in the chemical reaction, I'm going to do the math. And so these two numbers subtracted is 0.0037. Because my numbers are exactly the same in the second column, I should get exactly the same number. And now I have to do this math. 0 plus 2 times this number is 0.0276. So each of the rows do not, like, these rows do not add up to be mathematical. Like, they don't make mathematical sense, they make chemical sense. So it doesn't seem like this like it might not make sense to you mathematically. It should make sense to you stoichiometrically though. Okay, so now that I have all of this work done with my ICE table, what am I going to do? I'm going to write a KEQ for this. Okay, so remember how to do that. Products are on the top, and they're raised to the exponent. That is your stoichiometric coefficient. And then your reactants are on the bottom. And so now I can figure out what is going on with this chemical reaction, if it's product or reactant favored, by doing the math. Now the trick is we always use the E row to put the numbers into our equation.
So we use the numbers from that row.
From the E row of your ICE table. So you have to write down the I and the C so that you can figure out what E is. But then the only numbers you put, or the only values you put into this equation are the E ones. Because, think about why that is. KEQ is calculated at equilibrium, and so we need those equilibrium concentrations to be put into this mathematical formula so that the chemistry makes sense. When I did this problem, I think I got 55.6 as my answer. What's the unit for KEQ?
Is it none?
It is none. So this is your answer. And now, would this be reactant or product favored? Good. Okay, so this is the basic way that we use any, you can use any chemical equation and use an ICE table for it and calculate its equilibrium constant for anything. Yes, Donovan?
So you see like green, green, this 0.026. How did you get that?
This one here?
Yeah.
I did 2 times 0.0138.
Yeah.
Good question. Okay, so what we can do now is use this concept and what we know about KSP to figure out the solubility of ionic salts. So that's where all of this is going to come together. So KSP and ICE tables can be used together to calculate what's called the solubility of ionic salts.
Oh, we're not done.
Oh, no. We're not done. This might take the entire class.
You can I can't focus.
I know. I know it's gonna be hard. I'm doing my best. Okay. So the solubility is really just going to tell us the amount of the solid that will actually dissolve. Why is this useful? Because sometimes you really need a substance that's going to dissolve. Or if you're trying to make an electrolyte, you need to be able to know that it will dissolve in your water. So there are, many of you are athletes, right? What's the purpose of consuming electrolytes? Do you know?
Doesn't it help your body store more water?
It does, yes, it helps your body to recover faster because you can store more water, and it replaces the minerals that are lost by sweating. So if you were to be sweaty from sports ball and then you licked your arm, what would you think it would taste like?
Salty.
It tastes salty. And that's because your electrolytes are like come out of your body. The electrolytes like sodium and potassium and calcium, they come out of your body as sweat. Or they're part of what makes sweat. And so you need to replace those nutrients because if you don't have them, your muscles can't function properly, your heart can't function properly, and you can dehydrate much more quickly, and those are all not great things. It also helps prevent lactic acid buildup. Do you know why lactic acid buildup is bad? It causes muscle soreness or cramping, yes. Yes. So it's important to be able to have electrolytes. Not everything dissolves though in water. And so if something isn't going to dissolve, your body won't be able to metabolize it. It'll like go in one end and go out the other. Like corn. It's corn. Okay, so let's take a look then at how we're going to use KSP with the ice table. All right, I'm going to give you an example. Let's talk about barium sulfate. I know that its KSP is 1.1 times 10 to the minus 10. Your question is going to ask you what's the solubility of this compound. Okay, so I'm going to, in red, write the steps, like a step by step for what you need to do.
How long? How many pages is this going to take?
Don't know. Depends on how big you write. There are 6 steps for this kind of problem. Okay, so step 1, write your chemical reaction. And then obviously plus balance, because if it's not balanced, you're cooked. Okay, so you just turned in a homework for me where you wrote all of these chemical equations. So how do you write the chemical equation for barium sulfate? Well, you know that it's a KSP, and so that means that you start with a solid and you break it apart into its ions. So what's the charge of barium? 2+. And sulfate is 2-. Is this balanced? Okay, good. Make sure you have your states of matter because that is important. Okay, that's step 1. We're 1/6 of the way done. The second step is to write a KSP. You also got quite a good deal of practice on this because you just handed in a homework. And so your KSP should just be your two products. I'm sorry, I ran out of room a little bit. Any questions so far? This is all review. Now we're going to get to the hairy bit. Next step is to write an ice table.
Jeez.
Yeah, that's a little icky.
That was tough.
Okay, so I'm going to do that right underneath the chemical reaction that I just wrote. So ICE, that's a good start. I'm going to draw a line in between C and E because that helps me to, that helps me to remember that I'm going to have to do like the math there. And now for these types of problems, this is what your ice table will always look like. What's the concentration of a pure solid? Not quite.
Is it like infinite?
It is infinity.
Boom.
You are cooking today, Ray.
What was the What was the question?
What's the concentration of a pure solid? It is infinity. Okay, so then remember what we learned from a while back. How much product do we have before the reaction starts?
0.
0. So your I row will always look like this. Infinity, 0, 0. Okay, so now this is where things get a little bit tricky. Oh, gee whiz, I gotta stop doing that. Sorry, my bad. In the C row, we don't actually know how much will dissolve. That's what we're trying to figure out.
So we got sulfur annexes.
Yes. So we don't know how much of the barium sulfate will dissolve. So we're going to write minus X. And then we're going to solve for X.
No.
Okay, so just have patience. If you if you used 1X on your C row, gentlemen, if you used 1X, how many X's will be added of barium? Whatever your stoichiometric coefficient is here, if they're the same, this number will be the same.
What?
We'll do enough examples. Why is what backwards?
I wrote the equation backwards.
You wrote it this yields that?
Yeah.
Oh, flip it around.
What, now we're
Okay, so then how much of the sulfate should we add? Okay, so now let's do our math. What's infinity minus X? Infinity. What is 0 plus X? What is 0 plus X? Still X. Okay, our ice table is complete.
Wait then.
Okay, so again, the reason that we have X there is because we don't know how much of the barium sulfate will dissolve. Some of it will, but not all of it. And we just don't know how much. Step 4 is to put our values from the E row into KSP. Okay, so KSP equals barium 2 plus is an X. SO4 2 minus is also an X. So KSP equals X times X. Step 5 is the algebra. Solve for x. Okay, so x times x is also known as
Squared.
good. So how would you solve for x in this equation? Square root. X equals the square root of KSP. It'll never be as easy as this ever again.
Why?
Well, you'll see. It'll just get harder and harder.
What?
And I'm recording, so I'll refrain from using a dad in jail joke. Number 6 is to just calculate the value of x. So that just means put your number into the formula. And so I was given my number at the beginning, 1.1 times 10 to the minus 10. Take the square root of that. Let's all do that to make sure that we know how to use our calcs. There are a couple of ways that you can do square roots. You can take it to the 1/2 power, which is what I normally do, or you can just put it in the square root, whatever you want to do. You should get 1.0 times 10 to the minus 5. Anybody get something different on their calculator? Okay, you have to be worried about significant figures. So, how many did you start with? Well, 2. Remember, when you're given a number in scientific notation, it's only the things to the left of the x that matter. So that's why I have 1.0 here. But now x does have a unit. K does not have a unit, but x does. Because it's a concentration, your unit for x is always m. K has no unit, but x's unit is m. K has no unit, but x's unit is m.
Wait.
All right, how are we? We're doing bad? Let's take a small brain break and then we'll come back and do another.
Well, can I play one game?
Yes. We're gonna just press pause here. Let's do another example. This one I'm just gonna make up off the top of my brain noodle, but where did my pen go?
I think Charlie did too. Did he?
Does anybody see? Oh,
I didn't know.
Yeah, he's
It would,
usually that when he's at school.
Kind of all the time. He does it all the time. Really? I think so, yeah.
all right. Gentlemen, let's go through all of the steps and answer this question.
Right out the formula.
Here's our KSP. Okay, so your first step tells you to no,
Equation.
write the equation.
That's what I want.
You need your states of matter, so make sure you include those. What's the charge of aluminum?
3 plus.
3 plus.
3
I was
plus.
completely off.
You were. All right, what do we do with the NO3? What happens there?
Oh, yeah, bring it over.
3 NO3, good. And then what's its charge?
Minus.
Good. That's step 1. What's step 2?
Right.
KSP equals. What do we do with the 3 now?
Put it on
Exponent.
top of there.
Good.
Good.
Good. Okay. What do we do next? What's step 3?
Ice.
All right. ICE. Drawing my line. What should my very first row look like?
Infinity 0, 0.
Yep, that's always the same for these types of problems. Okay, so now what's different here, we're still going to always just subtract x. And then in my E row, I still will always have infinity. This column is always the same for all of these problems.
The I?
The I row is the
Oh,
same,
yeah.
but then the reactant column is also always the same.
So the L.
No, other way around. Yes. Okay, so now we have to look at the stoichiometry. If your number is 1, you are going to add plus x. Why? Because you are subtracting an x here, and there's a 1 here. And so if that's the same, your change row has to also be the same.
Also next one's 3.
But the next one is 3x. And the reason for that is because every time one of these breaks apart, you'll produce 3 of the NO3. So then 3x is your answer for the E row in that column. That was step 3, right? What's step 4?
Put values from 0 to KS.
All right.
100.
Okay. So now we have x times, but now we have a situation where we have 3x cubed
Why is it cute? Oh, wait, never mind.
because of that exponent here.
So what we do, I just want it down.
Okay, so now we have to apply the cube to all of the things in this parentheses. So the x will stay the same, but then what's 3 cubed? And what is x cubed? Well, that's x cubed. Okay, so now combine your x's, and you should get 27x to the 4. I do this. I have this bad habit where I just always write equal sign and I never write the thing. Okay, what's the next step?
Solve for x.
Solve for x. Okay, so to get x by itself, we're going to first have to divide out the 27, right? So I'm going to have KSP divided by 27, and that equals x to the 4. But is that what we're looking for? Do we want x to the 4? No. So how do you undo that? The 4th root.
Fourth root. Wait, what are we doing?
Have you learned this yet in math land?
Yeah.
Yeah, we're gonna probably.
So just take it to the exponent, your new exponent then will be 1 divided by whatever that number was. So easy.
Would you want it wrong? Just put like a root of 4.
No, that's an acceptable way to do it. So if you were to write this instead, that is acceptable. Your calculator, you can tell your calculator how to do that. I don't know how.
There's like 2 square roots and one is like an x.
It's math and then 5. Okay.
Thank you, Joe. Okay, so if you wanted to do it this way, we would type in our KSP. So go back and find your KSP. Okay, so that's the next step. It is 1.1 times 10 to the 5 divided by 27. So type that number in. Times 10 to the 5, remember, when you're doing times 10 to the 5, it's second and then comma. Divided by 27. And then if you go to, Joe said math, and then 5, you can type in, thanks for knowing that, Joe. I do it differently. I'll show you the way that I do it. And then you can just type in the numbers. Oh shoot.
What step is this, 5 or something?
I think this is 6.
No, let's go to 5.
Did you get 5?
I got 0.37.
I got 7.9.
Okay, hang on a second. I think I screwed up. I'm gonna do it the way that I know how to do it. 7.99?
Yep.
Yep, okay.
That's all steady.
Okay, so then what's your unit?
M.
How many significant figures? this is your answer.
That's complicated.
So that'll be the concentration of your ions at the end of your dissolving. This is complicated. That's why I said this is going to be probably the worst day of the year. Okay, how do we feel about this? Show me on your hand on a scale of 1 to 5, 5 being like this, I'm a boss at this, 0 being I hate my life right now.
0.
Dude, go put a big 0.
Okay, most people are above 3. I like this, well done. Let's do one more example and then I'm going to give you your homework and I'll show you some examples from there. Yes, ma'am? Oh, certainly. Is this enough?
I know how to do this.
With calculators? I'm going to restart again. Let's do one more example and then we'll do a bunch from your homework. All right, see, I want you to try to do as much as you can without me.
Okay.
Let's do barium phosphate. And I'm making up KSPs off the top of my mind. But if this is going to be a small one. Okay, so go through all of the steps and try to do what you can. I'm going to pause the video again and we'll come back with some answers. Okay, so before you go on, just check to make sure that your chemical equation and mine and your KSPs are the same. Because if you get this wrong, everything else necessarily must be in error as well. So that's why I spent so much time last time on the equation and writing KSP. Okay, so let's see how you're doing. The next step is the ice table.
You said something.
Infinity 0, 0, minus x infinity, plus 3x, so 3x is your answer, plus 2x, 2x is your answer. I'm going to put those numbers into my formula. Barium is 3x, and that's cubed. Phosphate is 2x, and that's squared. Ray noticed something really great. This number and the exponent will always be the same. So if you notice that you've got discontinuity here, that's a red flag that I've done something wrong. Okay, so 3 to the third power is 27. 2 squared is 4. So then 27 times 4 is 108, and it is x to the 5. To solve for x, you will have KSP divided by 108 to the 1/5 power or to the 5th root. However, this is the way I do it. If you want to do it like this, I don't mind. But just be aware that that's how I do it. What was my made up KSP?
5 times 1.5.
Oops. And so I got as an answer the same thing, Hunter, I think that you got 2, 0, 0.
Is it just 1 0 after?
It is just 1, 0, you're right. Thank you.
Wait.
And then my unit is okay, so
Getting these significant digits
from the K value.
Oh,
So since I made it up, it was just 2 numbers.
Wait, is it? What's the number that goes in the KSP?
It was
Oh, that one.
3.5 times 10 to the minus 12. Which I realize I just made up. We could look that up in a KSP table. Those are all known numbers. The values that I put on your homework are accurate. example from your homework so that we have something to look back at here. And then we'll call it a day. Let's start with number, actually I don't want to do number 1 because number 1 is pretty easy. I think you can manage that. Let's instead do number B. Or do you want to do C?
Let's do C.
Let's do C. C says that cobalt phosphate dissolves in water to the extent, oh shoot.
What was the answer to the last one?
Actually, the answer to the last one was 0.002. I did these problems actually backwards. So can you please turn to page 3 of your homework?
So much work.
I apologize. I forgot that I had done that.
This doesn't seem that long.
These are birds.
Okay, so we will learn how to do pages 1 and 2 next time.
So what are we doing? Just page
Let's do 2A.
A.
2A? Okay.
What pages are we doing? Just 3 and 4?
Just 3 and 4 for today, yep. Okay, so it tells me that the compound in question is lead 2 chromate, and it has a KSP value of 2.8 times 10 to the minus 13. My instructions say calculate the solubility of the ionic salts in molarity for each of the following. You must write a balanced chemical equation, a KSP expression, and an ice table for each problem. So that means you have to go through all 6 of the steps. Okay, so this is just the same as what we had been doing before. My first step is to write the equation. What's the charge of the lead here? It is 2 plus. How did you know that, Hunter?
CR for 2 minus.
And there's 1 of each. Yep, so lead has to be a 2 plus. Okay, super duper. KSP then equals PB2 plus times CrO4 2 minus. Ice table time. Infinity, 0, 0, minus x. How many x should we add for the lead? Just x. And for the chromate? Just x. Okay, so this is a nice easy one for us. Putting our numbers in, x times x, x equals the square root of KSP. Your significant figures will always be determined by what your KSP value is, even though that is a constant that's given to you, and you can't really control significance of that anyway.
Oh, this is too hard.
Okay, good. That's good. That's good. That means we did a good job today. So my significant figures are okay, but then remember, for these problems, if you're figuring out solubility, you need to have N, molarity, as your unit. KSP is unitless, but X is not. Okay, so now, show me on your, yes, Ray.
Where did you get the 28 from? Is that-
It was given to me in my problem.
Oh, yeah, okay.
I got -7.
Yes, yes, me too.
You almost beat them.
Okay, now show me on your hand scale of 1 to 5, 0 being I hate my life, 5 being this is good. Good, 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 good. Okay, good. You guys are feeling confident and good. So that you don't have to overwhelm yourselves next week, try to have, there are only 6 problems on here. So try to get those done for me for next time. I'm not going to check them, I'm not going to notice, but it'll help you if you can get a head start on those. No, it doesn't ask you for that.